Here we'll be using molecular orbital theory to determine the longest bond between a series of particular molecules. Now, when we are dealing with the longest bond, what we're really focusing more is on our bond order. Because information about our bond order is going to dictate a lot of things, such as a trend that is occurring here. So if I increase my bond order, that means my strength of the bond will increase. That'll also mean that my, where to put it? That also means that my stability will also increase as well. However, it also is going to mean that my bond length will decrease. So a bond order, if you recall when we were working with determining bond orders from Lewis structures, a bond order of 3 typically signifies a triple bond. A bond order of 2, a double bond, and a bond order of 1, a single bond. Well, this makes sense because if I'm increasing my bond order, the highest bond order that I could have is going to be 3. So 3 is a triple bond. If I drop down to 2, that's a double bond. My length is going to increase as I drop from 3 to 2, and that also means that my strength will also decrease as well. I don't need to put as much energy to break in a double bond as I would to break up a triple bond. So this is the kind of behavior that we're looking for. And if we're looking for the longest bond, what we're really looking for is we're looking for the lowest non-zero bond order. Now, the reason I state non-zero is that if your bond order is equal to 0, you will not make a bond. So what we really need to focus on is going to be making sure that of the molecules, if they have a non-zero bond order, we'll use those as a comparison. So going to our problem here, notice that I'm working with a nitrogen and an oxygen. Nitrogen has a total number of valence electrons of 5. Oxygen is always 6. So I will have 11 electrons to work with. But since I'm working with ions, let me just go ahead and make a grid to just write down how many electrons for each molecule that I'll be working with. So NO in the middle is 11. As I become more positive, I'm decreasing the number of electrons because I'm popping them off. So NO positive is 10, NO2 positive is 9, and if I have a negative charge, I'm adding electrons like 12 and 13. Now, since we're dealing with bond order, I know bond order is going to be the number of electrons in my bonding region minus the number of electrons in my anti-bonding region. Divide that value by 2. Now, if I have more than 4 electrons in my total number of valence electrons, I know that those first 4 will be used in my 2s splitting. But this also means that those first 4 will not factor into my bond order because they've already been neutral. They're already, taken care of with the anti-bonding and bonding sigmas from that 2s. So what I suggest that you do is that you subtract by 4 to already account for your 2s's being used. So take your number of valence electrons, subtract every single one of those by 4. So 9 minus 4 is 5, and then just 6, 7, 8, and then 9. Now, this is essentially a little bit of a cheat, but this is allowing me to focus only on the splitting that's occurring to my 2p's. So those, the minus 4 values, so like 9, 8, 7, 6, 5, I'll be using those to figure out what my splitting would be with my 2p molecular orbitals. So here's my energy level if I had all of my atomic orbitals being used. And now I need to determine whether or not I will have high sp mixing or low sp mixing. Now, if you're still a little confused as to what you're looking for, you always want to base your sp mixing on the most electronegative element in the molecule. And in this case, we'll be working with oxygen. Now, this is going to mean one big thing. With oxygen, we'll be working with a small or low value of sp mixing. What I'm really telling you with this is going to be that the energy associated with our bonding sigma is less than the energy associated with our bonding pi bonds. So I'll go ahead and put my bonding orbital there and then my sigma below it. So those are my 2 pi's, those are my bonding sigma there, so I have those energy values there. Notice that they both sit below the atomic energy level. However, for my anti-bonding, we're going to flip it above it. So the next highest energy level after my atomic will be my 2 antibonding sigmas, or my 2 antibonding pi's, which is just pi asterisk. And then above that will be my 1 antibonding sigma. And that's what I'm working with there. Now, notice, again, the bond order is the number of electrons in our bonding region. So the most that I could have here is 6, because I have 3 boxes, 2 electrons per box. So at most, 6 bonding electrons. So notice I have an NO positive here. That's exactly 6. So that would mean that all of my electrons are going to be bonding. I'll have nothing in the antibonding, and I'll divide that value by 2. So this would mean that my bonding order, if I used up only 6, would be 6 minus 0 over 2, which is just 6 over 2, which is 3. Anything lower will be 5 minus 0, or 4 minus 0. So if I know, I'm just going to extend my grid out now to include the bonding order, because I know with 6, the bonding order is positive 3.0. With 5, I will still not have anything in my antibonding. It'll just be a value of 5 minus 0 in the numerator. Divide that by 2 is a positive 2.5. However, look at NO. I have 7 electrons, which means 1 of those electrons will be in the upspin position in my antibonding. So for 7, it'll be 6 minus 1. So 6 bonding electrons minus 1 antibonding electron. 6 minus 1 is 5, divided by 2 is 2.5. For 8, so notice that there's a trend happening here. You have a maximum value of 3 for your bonding order. And then from there, you're either going to get bigger or get smaller. So as the number of electrons, number of valence electrons increases from beyond a bond order of 3, your bond order starts to decrease. So I can now tell you what my most stable is. It's my NO positive, because it has a value of a bond order of 3. My least stable is NO2 negative, because it has the smallest bond order. But the question asked us, which one is the longest bond? And as I mentioned, we're looking for the lowest bond order. So the answer to our problem is going to be NO2 negative. According to molecular orbital theory, when you draw these all out, based on the sheer number of bonding electrons to antibonding electrons, NO2 negative will result in the longest bond compared to all 5 of these molecules.